Okay, welcome to this session and the third International Congress on Human-Computer Interaction, Optimization and Robot Applications. My name is Mehmet Emir Köksal. I have been working for 19 Mayıs University located in Samsun, still located at the Black Sea part of the Turkey. In this session, we have nine presentation. The duration of each presentation is 15 minutes, including question and remarks. The first two presentations will be given by Dr. Veselin Chobanov. Stanislav, his first talk is Power Quality and Financial Risk for RES Investments. Veselin, you can start.
Thank you very much for the room. Okay, I'll talk about the first paper is about power quality and financial risk for renewable energy sources investment. This is very important topic because a lot of renewables are coming these days, and the risk between new installation and existing one are related with voltage increase, which can lead to switch off of this installation, and this can lead to financial losses of all participants in the network. In fact, the connection of new renewable sources and their unpredictability of the electricity produced creates a lot of problems in the functioning of the electricity system, which, as I mentioned, are related to voltage regulation and ensuring the stability of the network, also harmonic distortion in the system, and some other issues. This problem will increase in the future due to the expected dynamic increase in number of newly built renewable sources. The problem with them is that these new generating sources are coming without active management. They are risky from the point of view of normal functioning of power system, because any unacceptable deviation of voltage from standard leads to their temporary automatic shutdown. And the notification regime, which is coming this day, has a negative impact not only on the quality of electricity supply, but also on the project economic return, both of new and already connected renewable sources. These problems are very important, and they are subject of this research. There are several boundary conditions. I assume that when performing the calculation procedures related to assessment of impact of this renewable capacity on the voltage in the distribution network, the connection of renewable plants and the traditional plants, both of them will continue to operate. We have also not forgot that the existing power plants are connected to the system after assessing their impact on the quality of electricity. For the new installation, especially for those with small capacity, the regime is a notification regime. So there is no assessment on the impact they will have on the network. I also assume that the new electricity capacities will be connected, as I mentioned, in the notification mode to the distribution company. Also, with the connection of these generators, of course, the voltage will increase, and this process even more pronounced in areas with low electricity consumption. And in this regard, when assessing the impact of newly introduced renewable sources to the network and sizing of the electricity distribution network, I use two boundary conditions. The first one, zero consumption and full generation. And the second one is full consumption and zero generation, because these are the conditions that we can assess. In order, I have in mind also that in order each user to have the corresponding quality of voltage in the substation, there is an automatic voltage regulation which increase the voltage, and this increase corresponds to 3% or 7% of allowable deviation remains. We all know that the deviation that is given from the standard is plus minus 10%. So the voltage regulation range in medium voltage substation is plus minus 400 volts, or this is 2%. And in this sensitivity range, the automatic voltage regulation is not activated and the step controller does not switch. And this of the permitted deviation of 10%, 5% remain for distribution network, which in absence of other rules are distributed. For low voltage network, I use 3%, less or equal to 3%. For medium voltage network, 2% equal to 2% or less than 2%. You can see the formula for voltage deviation that I use presented on the screen. For the non-produced electricity, this is the key component, because this is the energy that is lost, and this is key element because the investors make their financial plans on the basis of power stations that working on full time. And that's why I calculate the energy that is lost. And this lost energy is in fact in periods where there is a lot of sun radiation, but low consumption. And in this case, these renewable energy sources are automatically switched off from the distribution network. Here you can see that for electricity grid, we have two voltage levels, low voltage and medium voltage. I have in mind that for the grid, all power plants are the same. There is no algorithm, in fact, which power plant is connected today is or new, or we have power plants with long-term contracts. In fact, you can see from these calculations here that even very small new power plants like 30 or 60 kilowatt can result to normal increase of voltage, which will result in switching off not only the new capacities but also the existing ones. Okay, the impact of these new renewable sources on the network is very important, because it is obvious that in the periods with low consumption, which are in fact in most isolated regions in the period from 1 to 2 o'clock, and from 3 to 4 o'clock. At this time, we have a lot of energy produced, but the consumption is lower. And when we calculate what is the unused energy, in fact, it can reach around 20% of the production, uh, the production that is included in the financial results. And this reflect internal rate of return of investment. And normally for most installation, this internal rate of return is around 9-10%. And having in mind this, the reduction is around 30%, which means additional 1 to 3 years of a payback period, which is not a very good, especially for customers who has long-term contracts, because they have fixed periods for their contracts, and they are not increased with the periods of interruptions. And from this point of view, every new installation which is connected to the network in this notification regime without assessing the impact on the network will result on around 30% of reduction of the income, not only for the new installation, but also for the installations that are already connected to the grid and which already has long-term contracts with this preferential feed-in tariffs. So as a conclusion, I can say that this increase in share of electricity from renewable energy that is expected in the next 10 years. For Bulgaria, this is around 10 to 15% for the next 10 years. And this will lead to financial losses, not only for the new investors, which want to participate on the liberalized market, but also for those who have already connected to the network. And yes, this is very, very important problem. And yeah, these are the results. Thank you. Do you have any questions?
Thank you very much for your talk. Is there any question, comments, or remark? No question. Okay, the title of his second talk is Electrical Infrastructure in Hospitals, Risk and Opportunity for Quality Healthcare.
Yes, this paper is important from the point of view that in the recent years there is a technological boom in the development of a lot of diagnostic equipment in the medical field, which in fact means that we have very complex technologies that are used for precise diagnostic and therapy. Of course, this leads to better results, but very often these new technologies are connected to the electricity networks in the hospital, which are more than 30, 50. Some of these hospitals are even 70 years old. The increase of consumption of energy in the hospitals, and this new equipment leads to several risks. When we have especially a situation like we have today with the COVID-19, this additionally increased the electricity consumption in hospitals and increased these risks. In fact, in the last year, I make several measurements in 10 of biggest hospitals in Bulgaria, and I can say that almost all installations in this hospital have been in operation for more than 30 years. And despite the relatively good technical support, a significant part of this medical equipment is in a permanent state of emergency due to low reliability of the internal electrical network of the hospital, and this leads to interruption of the hospital process and deterioration of the quality of the medical care. Uh, and if we want to improve the reliability and quality of this medical research, this requires following major issues to be addressed in the timely manner. Uh, the first one, renovation. Renovation. Uh, as I mentioned, the studied hospitals started their active life more than 50 years ago. And since then, they have continued to grow, expand, and open new medical wards and support facilities. Um, Medical and auxiliary electrical equipment has been also constantly changing without updating the electrical infrastructure. Uh, in most places, they have not been taken into account and is not assessing the technical parameters of existing and non-renovated electrical installation. And this results on the quality of the results of medical examination, which is very, very important and happens very often. You can see on the pictures what was the basic electrical equipment of the operating theater 50 years ago, and what is the common electrical equipment now. You see a lot of improvement is already done, but most of this new equipment is connected to the old electrical networks, and the results we have are not with good quality. We have also technical unsuitability of the electrical system deteriorates not only the quality of electricity, but also condition. And there is room for accidents to electrical equipment that endanger the lives of both patients and also medical staff. The paradox is that medicine and related technical solutions of new generation are not accompanied by adequate innovative solutions of the electrical engineering infrastructure, which is designed according to the standards of the last century. And today it is irretrievably obsolete and does not meet the high requirements of modern medicine and the implemented modern medical equipment, and the accidents resulting from a short circuit, for example, in any operating room leads to loss of life, not only for the patient, but there are several cases that medical team has also problems, and this was due to equipment fails. When optimizing the cost for maintenance of electrical infrastructure, all unplanned connection of new medical devices has leads to risks because this in fact, in a daily basics, there's an accidents, burning of electrical equipment, which is associated in addition to overspending, overspendings also with loss of valuable medical information and reducing the efficiency of medical teams. It is not the exception in cases when both X-rays, for example, of one of the examined hospitals due to accidents do not work for more than a week. And also the data for the measurements shows that the reason for this are not so much in their physical depreciation as the deteriorating parameters of the electrical equipment and the unplanned increase in the installed capacity in the hospital. Some other issues and accidents in these facilities are usually accompanied by significant adverse consequences, prolonged power outages of large parts of the hospitals, termination of its main functions. Also, there is a lot of trouble shooting without complete documentation is also associated with a high risk. Problems arise that endanger the safety and lives of patients. The effective management that was part of this study also shows that almost 40% of electricity is losing due to improper grading of electricity networks in hospitals. What else? When we're talking about the generators, the reliability of generators that have to provide the backup, there is a lot of problems there also because the reliability is checking normally by starting it daily. However, this is contrary to accepted reliability criteria, and it is difficult to accept the notion that in case of interruption of external power supply, that the generator will reliably and qualitatively cover the needs for electricity. There are several more significant reasons for this. First, because the procedure for checking the reliability of generator, which has been adopted by studied hospitals, does not meet the modern requirements. And secondly, because the use of physically and morally worn generator to cover sensitive loads, such as those of medical electrical equipment, is not a viable method to quality power supply. And third, they are not tested at idle conditions. What are the opportunities? There are also a lot of other problems that exist, but I don't go in details in them. I will focus a little bit on opportunities that the liberalized market of electricity gives to these facilities. There are a lot of opportunities for optimization of electrical costs. To a large extent, there are two approaches, in fact, with a strong applied value to which the management of hospitals must adhere. In one approach, through the introduction of a new investment policy, the consumption of electricity is limited. In other approach, it can be considered as a conservative approach. And here the aim is to maintain the achieved level of electricity consumption. The first innovative approach is with the focus on limiting electricity consumption, which involves conducting a detailed audit of the hospital and developing a strategic innovative investment program aimed to upgrading equipment and increasing the energy efficiency. The second one approach aims to maintain electricity consumption by using the opportunities provided by the liberalized electricity market. And when we combine these two approaches to reduce electricity costs, combined with the use of one's own source of electricity, expands the possibilities for additional flexibility and to achieve significant reduction in electricity cost. We can also combine this with an accumulative system expands, which also expands the possibilities for consuming management. When forecasting the volume of electricity consumed, it is essential to assess how manageable the risk is and the increase and decrease in consumption. is associated with various factors, some of which do not lend themselves to quantitative measurements. For example, the pandemic situation, in addition to medical challenges, generates a number of economic problems related to the uncertainty of forecasting energy consumption and related costs. In the pandemic period, in most sectors, there is a decrease of consumption. You can see this. You can see this here, on this table. I make a study for different sectors in Bulgaria during the last year, during the pandemic situation. You can see that in all sectors there is a decrease in energy consumption. But the data shows that on one hand we have this decrease, but on the other hand, as you can see on the figure 4, the consumption for hospitals is increasing. All 10 hospitals that were studied, not only for the problems with their electrical installation, but also for their consumption of energy during that period, shows that during the pandemic, on the one hand, we have this general decrease in electricity consumption, but on the other hand, specifically in hospitals, electricity consumption increases, which increase the need of reliable supply and its redundancy. As a conclusion, I can say that we are witnessing enormous advances in medical science. The use of more and more electronic devices that improve the research, diagnostic, treatment of various diseases is without alternative. Of course, ensuring a stable and reliable environment for normal functioning of this medical equipment requires hospital managers, especially, to permanently upgrade not only the equipment, the medical equipment, but also to upgrade the electrical infrastructure that serves it, because all of the problems that we discuss today, they exist in all of these hospitals. And yes, this bad infrastructure in the hospitals leads to wrong results when testing is provided, but also leads to losses of human lives. The managers of hospitals can have two benefits. The first one is to increase the quality of the services they provide, and on the other hand, they can improve their financial stability by using the resources that the liberalized market of electricity provides, because they can use these opportunities and they can reduce the losses that have for additional energy they use, which in fact is not necessary to pay for. Thank you very much for your attention.
Is there any question, remark, or comment? No question. Thanks again for your presentation.
Thank you very much.
Next speaker is Dr. Sayed Ibrahim Ismaili. The title of the talk is Design and Assembly of a Smart Recycling Bin.
Thank you, Dr. Mohammed. Now, can I share my screen or?
Waselim, could you please stop sharing your screen?
Okay.
Okay.
Yes, I did.
Thank you.
Thank you.
Okay. Now you can.
Yes, thank you. So good morning, everybody, and welcome to this presentation, which talks about the design and assembly of a smart recycling bin. This project is a capstone project that was done by our 3 undergraduate students at the American University of Kuwait, namely Maryam Maqsid, Farah Abdel Salam, and Sarah Al-Aswad, under my supervision. A major factor of air pollution in urban cities nowadays is burning waste. Recycling is the process of collecting used materials, commonly known as waste, and creating new products to prevent the waste of potentially useful materials. Recycling includes different material types like glass, paper, metal, and plastic. The proposed recycling bin will namely filter objects made of glass, metal, and plastic. One of the ways to reduce waste, as well as the costs associated with recycling, is to filter the waste according to the material type, starting at the source, that is, the people at homes. The design of a smart recycling bin called EnviroBin is proposed. EnviroBin filters the waste according to the following categories: glass, plastic, and metal. We have reviewed around 8 similar projects to extract the main features, characteristics, and the components used. As you can see, all of the projects use sensors to filter out different types of materials. And these sensors are controlled by mostly the Arduino microcontroller, which takes the data from the sensors and moves the motors to move the waste to the according bins. Some of the projects use RFID to read the paper waste or the plastic waste, note the type of the material, and then filter it and drop it into the respective compartments. Some of the projects use Wi-Fi connection. In our project, we are using the Bluetooth connections. Some of the bins also that are used outdoors use GPS, because sometimes if you have high wind or floods, the bin can move from one place to another. So having a GPS will help you know the exact location of the bin. The proposed prototype has 4 compartments, 3 of which are for glass, plastic, and metal. The last one is for unidentified material type. An infrared sensor is used to detect if an object was placed inside the recycling bin. An inductive sensor is used to determine metallic objects, and a color sensor is used to detect glass objects. A unified color, mostly white, is assumed for simplicity. The capacitive sensor is used to detect plastic waste, and the control unit used is the Arduino Uno microcontroller. We have 2 stepper motors used in the implementation of the prototype. One is used to move the conveyor belt, as we'll see, inshallah, in the following video, to the left or to the right, according to material type. And the second stepper motor is used to move the wooden handle forward and backward to push the waste into their respective compartments. This figure shows a simplified system architecture. You see at the top, we have the waste or the different materials dropped. Then we have the different sensors to detect the material type. This information is fed into the microcontroller, which in turn will move the stepper motors either clockwise or counterclockwise. And also the wooden handle in the cases of the metal and the unidentified objects will be moved forward to drop these waste into their respective compartments. Also, what is not mentioned here, that in every compartment, we have also an ultrasonic sensor to detect if the compartment is full. If the compartment is full, we have an LED that will turn on, and also a message that will be sent to the user informing him or her that the compartment is full and needs to be emptied. This table specifies the components used in the implementation of the proposed smart recycling bin. Of course, you can see that the total cost is around $800. This excludes the design of the prototype itself. The bin, as you see in the following slides, is made out of wood, okay, and that design is not included, or the cost of that design is not included in this table. This figure shows the placement of the sensors in the proposed prototype, and this figure shows the prototype of the smart recycling bin. On top, we have the sensors to read and filter and decide the type of the waste. And here we have the conveyor belt that can move to the left to drop glass objects, or to the right to drop plastic objects, or somewhat to the left for metal objects. In this case, the wooden handle, as we'll see in the following video, will move forward to drop the metallic objects into this compartment, or a little bit to the right to move the unknown objects into the unknown compartment. After testing the prototype, it was found that the inductive sensor has a high efficiency. Metal objects were sorted correctly with around 100% efficiency. Due to the reduced efficiency of the capacitive sensor in detecting plastic, it was replaced with a color sensor. The color sensor was programmed to detect non-plastic objects, that is with color green, blue, red, and black. This resulted in an increased sorting efficiency for plastic from 30% to 70%. If one or more of the compartment is full, the proximity sensor in that compartment and the LED connected to it will turn on. It will also activate and update the mobile application via the Bluetooth connection. The MIT AI2 platform was used in order to create this application for Android operating systems. The main objective of the application is to notify the user when a certain compartment or more needs to be emptied. This video shows the functionality of the proposed smart recycling bin. You can see here that the wooden handle is being moved forward, but the motion is a little bit slow. Hopefully this will be fixed in the future. Future work includes, but is not limited to the following: using an array of sensors to increase the efficiency of filtering different materials. In this case, we can get the reading of several sensors at once, and maybe take the average of the sensors, the average reading, and go with the highest average. Waste in the unknown materials compartment can go through another cycle of filtering to increase the efficiency. And if the enviro bin was to be used outdoors, we can add solar panels and also GPS to the bin. Thank you all. That's it.
Any question? Comments or remark? No question. Thank you very much for your presentation.
Thank you, Dr. Mohammed.
The title of the next talk is Calculation and Mitigation of the Magnetic Fields under the High Voltage Overhead Transmission Line. That presentation is given by Salah Edine Hoçer. Salah. Present or absent? So he's absent, then we are continuing from the next presentation. The title of the next talk is Improving Training Time in Capsule Neural Network. The name of the speaker is Mario Chaydica. Mario?
Yeah, present.
Okay, now you can start.
Okay. Can you see my screen?
Yes, we can.
Okay. Good morning.
Yes.
My name is Mario. I'm presenting a paper titled research entitled Improving Training Time in Capsule Neural Network. With the invention of neural networks where computers try to behave or think like humans, the research has been on for a while, and a particular neural network called convolutional neural network had to become the best neural network available, because for all the data available, it was almost perfect. But convolutional neural networks had one particular problem. It had what they call the Picasso effect. When an object is shifted or tilted, either by its position or its pose, convolutional neural networks always had an issue identifying it. So Professor Hilton came up with capsule neural network. So this was kind of the solution of the problem, or the solution of the problem of convolutional neural networks. And he first talked about it in 2000 when he described an imaging system for the combination of segmentation and recognition into a single inference process using parse trees. But in 2017, his team wrote a paper on a dynamic routine mechanism for capsule neural networks. So that was kind of what gave birth fully into capsule network. So capsule neural network is just, it's simple. It's an artificial neural network whose purpose is to improve or design hierarchical relationship. Its purpose is to try to make machine work like a human brain. CapsNet attempts to mimic the biological neural network. That's basically making a computer think. You know, the idea of a computer before is garbage in, garbage out. Whatever you give to the computer, it gives to you. But right now, they are trying to make the computer evolve. They're trying to make the machines now think for itself. And we've gotten to the extent of all these driverless cars and the rest of them. With almost every design also comes a problem. And the problem with the capsule neural network for now is timing. The time it takes to train the data given to it is a little bit on the high side, which makes it a little bit difficult to implement a real-time application. For instance, if we need, let's say, to identify a person at the airport using a capsule neural network, it will take a long time to identify the person because it takes a longer time to train. So by the time, when the training is done, before the identification can be done. But because it takes a long time to train, it takes a little bit longer process to be done. So after Hilton had done his work and then started the convolutional neural network, different researchers around the world have started trying to look for ways to improve or make better the capsule neural network. So somebody from Korea named Choi had a method, a model, and his own model changed the model of Hilton. What he did in his own work was he changed the attention routine and the capsule activation. What he did was to change the dynamic routine and squash activation used by Hilton, and in his own he used attention routine and capsule activation. So this changed entirely the process of which the model of the capsule neural network actually works. But in the long run, actually did reduce the training time. So what our research did now was to further try to improve what Choi's work did. And this was our own contribution. What we tried to do was to look at regularization as a technique in machine language. And what regularization does is to help reduce overfitting by penalizing complexity. So with our design, we try to share the regularization decoder across each deep capsule. So each of the hidden layers inside the inside the capsule neural network, we have to share a regularization decoder in each of them. So when the data to be trained comes in, it did help reduce it. We also looked at the feature map, combining colors with convolutional filter, the did operation or convolutional operation on them. We also did this for each of the hidden layers. So this actually did reduce the spatial size as the color size of the data coming in, and did reduce the parameters. But what we lastly did was to add the losses, because at the end of the network, we have where the losses are added to get the actual image you are looking for. And we actually have a reconstruction loss and the margin loss. So what we did with our Python program was to add these losses together to make it one single loss. And this now actually reduced the parameters from about 9.5 million to 3.3 million. So this is an overview of our new model. So when the data comes in from the input, the first convolutional layer, we have a convolutional operation on it. So it have the same operation on the primary layer and the 4 hidden layers before we get to the full convolutional caps layer. Then at the end is where we add the losses to give out the output. So this is the overview of our model and our design, which looks like the choice model, but we added those 3 things, those 3 features to the architecture itself. So generally the architecture is the same, but just the internal configuration was what was amended and touched on. And that's why we're able to have this new one, which we have succeeded in doing. So what happened is that the model showed a comparative accuracy with fewer parameters and did reduce it from 8.2 million parameters to our model having 5.285 parameters. And when tested, it did show that yes, for mixed data set and CFA data set, we were able to get a faster training time per epoch for each of the models there. So this table now shows what we got now for the accuracy and the training time. For the accuracy, our model was much more better than Hilton's original model. For the mixed data set, we had 99.17 accuracy. For CFA10, we have 80% accuracy, and AFSNet, because we tested with these 3 data sets, we got 95.1. Then for the training time, we also had an improved timing for each epoch. For capsule network, we had 180 for MNES. Then for the AR, that is the original choice model, we have 51 seconds per epoch, but we have 34. So across the board, we did have an improved model, both for the training time and for the accuracy. So, so in conclusion, these changes made, these contributions made to the original architecture of the design of capsule neural network did actually go a long way to reduce the training time, and therefore will help give them a faster output when it's used for a real-time program. Thank you. So any questions?
Is there any question? Comment or remark? No question. Thank you very much for your presentation.
Thank you very much.
Okay. Now, the title of the next talk is Implementation of Pick and Place Algorithm for the Proposal of Water Handling Robotic Simulations. Name of the speaker is Nikolai Bratovanov.
Yeah, hello. My name is Nikolai, and so I have to share my screen now, right?
Right.
Let me see how it. Oh, okay, I saw it. Share screen, and we are waiting. So do you see?
Right, right.
You can see my presentation.
Right.
Okay, thank you. So my name is Nikolai Bratovanov. I'm from the Technical University of Sofia, Bulgaria, from the Faculty of Automation. And the topic is implementation of pick and place algorithms for the purposes of wafer handling robotic simulations. So this work is related to the field of semiconductor device manufacturing, which is a specific industry where those so-called wafer handling robots are used. So they have been aiding this industry for more than several decades already. And the purpose of those robots, which you can see here on this picture, is to transport the silicon wafers, which are used as a basis for the manufacturing of all those electronic devices, all those chips like sensors, processors, and whatever. So this all takes place in a specific industry, which where superior demands and requirements must be met, like most importantly, cleanliness, accuracy, and reliability. So everything, at the same time, everything has to be very fast, motion has to be very smooth. And this makes the tasks for the robots very challenging. So obviously the main purpose, as I said, of those robots are to transport the wafers, the silicon wafers. And we refer to this process as the wafer handling process. And so in this regard, specific end effectors are used, which are most frequently based on vacuum, and they grasp the wafer and transfer it between the different stations, as we call them, different process stations where specific processes are taking place in the process of manufacturing the chips. So the purpose, actually, I have a movie. I hope that you can see it. I have a movie which demonstrates the functionality of those robots. And here you can see the actual wafer handling process. So the purpose of this work, the project, is related to simulating this functionality. So in my previous work, I have been working on this simulator, this wafer handling robot simulator, which is based on SolidWorks API. It uses those 3D models. It is based on Visual Basic programming, where we actually simulate the motion of the robot. And we wanted to improve the functionality of this simulator by introducing the wafer handling process. We want to manipulate the wafers in this virtual SolidWorks environment. So this is the main goal of this current project. And I'm going to explain how this is realized. So basically, this is the most important step, where the wafer handling process has to be formally described. It has to be modeled. And in this regard, several algorithms are developed, which are later adapted and implemented to the SolidWorks API and to the SolidWorks API-based simulator. And finally, this approach has been experimentally, it has been verified with the help of several simulations. So in order to do this, of course, we need to get familiar with the real world wafer handling process. So what happens in the real life is the following. So you can see the robot here, and you can see its end effector, which, as we execute, we call it the get command. So we execute get command from station A, for example. And what happens is that the robot it approaches this station. It goes below the wafer. And at this moment, we have this vacuum sensor inside the end effector, which becomes active. It switches on the vacuum valve. So basically, the end effector is capable of grasping, sucking the object. And finally, the end effector starts moving in the vertical direction slowly. And as soon as the wafer surface is sufficiently close to the surface of the end effector, naturally the process of grasping occurs. So this is what we want to simulate as realistically as possible. We want to actually we have to monitor, to observe how close the gripper, the coordinate system of the gripper, is to the coordinate system of the wafer. So this is our first condition. We need to monitor this this state. So if they are sufficiently close, which is determined by several basic mathematical expressions, vector-based calculations, which you can see here. And also we need to monitor a second condition, whether the vacuum valve is on or off. So if those two conditions are met, are present, like this, we have that we are sufficiently close in the vertical direction, in the horizontal, in the plane. Also, the orientation of the wafer and the end effector is like identical. Then we check the state of the vacuum valve of the end effector. And if those conditions are met, then we consider that we are having the wafer handling process on, which means that the wafer and the end effectors, they start moving as a single component. So this is the whole idea. And as soon as we have those this vacuum sensor on, this relationship is maintained. At the moment of this sensor becoming 1, which means the vacuum is off, then we break this relationship, which means that the wafer is no longer attached to the end effector. So this is how we perform the simulation procedure, and obviously it is very close. It matches the real world case. So all this has to be those algorithms. Of course, they have to be implemented to the Visual Basic code in the simulator, and then everything has to be checked if it is working. So we start the simulator, and this is happening continuously. We have this motion loop where we continuously obtain the geometry. For example, the geometry of the position and orientation of the end effector, the position and orientation of the wafer. Also, we have this other device which is called pre-aligner, which also has handling capabilities. So the wafer can be handled by this chuck here, and this device is used for finding the perfect center and the specific orientation of the wafer. But of course, the principle is absolutely the same. It doesn't matter if it's going to be the end effector or it is going to be the pre-aligner. It's just a different coordinate system that is being checked. So this geometry is obtained. We read specific reference parameters which are compared to those like vectors calculated in the previous step, and we also continuously read the state of the vacuum valves, and if everything is as presented, then we perform the pick or place activity of the robot, and this happens all the time. It is continuous process. So this is the idea, and it was verified with the help of this particular 3D model, this particular layout, where we have the robot, we have the pre-aligner, we have 2 wafers which are being handled from the different stations A, B, and as expected, everything seemed to be working just fine. We also had to test the pre-aligner wafer handling functionality, whether the chuck is capable of rotating the wafer, of grasping the wafer. Yeah, and the results confirm that this approach which has been adapted to the SolidWorks API simulator, has been successful. So we have proper execution of the wafer handling procedure. We have successful wafer pre-aligning simulation. We rotate the chuck and the wafer goes, rotates with the chuck as in real life. And so this is to make sure we had to monitor what was happening with those reference parameters in the real time, and basically everything seems to be working. And I have a short video which it demonstrates the you can see the wafer handling simulation functionality. So those are SolidWorks models of the different robots. So this approach, it was adapted, it was utilized with different systems. As you can see, it doesn't matter what the robot type is. The principle is pretty much the same. So you can see the successful wafer handling simulation. And of course, this is extremely useful for various purposes, like complete analysis of different customer tasks, like different automation layouts. It is useful for offline programming purposes. It is also useful for marketing purposes. As you can see, those animations, those movies are very they're very useful for example, sending them to customers and showing what the future system, the potential system, is going to look like. And also obviously the functionality of the existing simulator has been extended, increasing its versatility, precision, and effectiveness. So this is the work, and as future developments, I have been pointed out implementation of other robot gripper types. We have different end effectors, which are not based on vacuum, but based on mechanical gripping the end effector, or based on the Bernoulli principle. So we need to figure out how to adapt the algorithm to those end effectors. Also, we have end effectors which flip the wafer in the process of operation, and we also would like to establish a complete simulation of the wafer pre-aligning process. So those are one of the future developments which I'm planning to do. So thank you very much for the attention. If you have any questions, please.
Thank you very much for your presentation. Is there any question, comments, or remark? No question. Thanks again for your presentation.
Sure, thank you.
The next speaker is Federico Insero. The title of the talk is Brain-Computer Interface for Human-Robot Interaction in Industrial Applications.
Good morning, everyone. Can I share my screen?
Sure.
Okay. Okay, can you see my screen?
Yes, now yes.
Okay. Good morning, everyone. I'm Federico Insero, a Master of Science student at Politecnico di Milano. And today we present the work called Brain-Computer Interface for Human-Robot Interaction in Industrial Application that was done in collaboration with the Università di Pavia. This work proposes an interaction strategy based on BCI in a collaborative robotic workstation. This presentation is composed by 5 main parts. First of all, a brief introduction regarding cobots and the features and the collaborative strategies that are applied in cobots. And this is very explained in the state of the art. Later, we propose our algorithm, which is an hybrid implementation between 2 collaborative strategies. We talk about our experimental setup that is used in our 2 case studies that are used for testing our algorithms. In the end, we'll draw the conclusions about our work. So why we are using cobots? The cobots are designed for be collaborative and safe. So they are mechanical design and programmed in order to work with human operators. Also, the features of cobots are that they have to join the features of machines, so the repeatability and the accuracy, with the features of the human worker, like high dexterity, their experience in their jobs, and also the solution-oriented thinking. Also, the efforts of the latest years are focused on design new methods in order to program more flexible applications in an easier way, the robots, in order to, I can say, design more flexible and more complex application for robotic field involve the robotic field in the industry. So now we are trying to focus on the collaborative features, and we try to work about an interaction strategy and how the robot and the human can interact. So these interactions is composed by two main parts. First of all, the human should be able to interact with the robot and modify its own task. And also the robot should be aware about the robot presence in the workspace. So this is done by means of two components, a communication strategy and the user interface. The communication strategy involves different technologies that can be used. The first one is the most simple, and it's always used for program robots and control them, is the teaching pendant. And also the gesture recognition can be used. Is not so spread as the teaching pendant, but both of them require that the user use both hands for controlling the robot. And this can't be suitable in most of the industries because the operator generally use his hand in order to work. There is also the voice recognition, which solves the problem of the before mentioned technologies, but all the industries generally are very loud, so the voice commands can be misunderstood. So we try to focus it on brain-computer interface. The brain-computer interface can be used in order to acquire signal from the brain and use them in order to interact with the robot in a more flexible and easy and most important, in an intuitive way for the operator. So there is not it is not required a training for the operators. So these can be more fast to use. So in literature are described the 4 collaborative strategy. The first one is the less collaborative, where the robot and the operator works in an independent way. So they are working on different work pieces and on different processes, but they are sharing the workspace. So all these collaborative strategy that can't injure the human operator. There is the simultaneous one where the workpiece is the same for both robot and the operator, but they are working on different processes. And also the sequential one, where the two processes are happening in different moments. We'll try to focus on the supportive one, where the two tasks, the task that the operator and the robot are doing can happen at the same times, and the action of both of two influence each other. So there is a direct consequence of the actions of the two robots, of the operator and the robot. These can be useful to exploit because creates a good partnership between the robot and the operator. So we can see a robot as more as a partner than a machine. So the algorithm that we propose that involves the supportive task is can happen, for example, when the robot requires help. So in the case the program on the robot encounters some exception, the robot can be assisted by the human in order to solve the task in a more intuitive way and without stopping the program of the robot. This hybrid interaction is we call hybrid because generally the task of a robot can involve an independent collaborative strategy where the robot and the operator are doing different tasks. and there is a moment where the robot requires assistance, where there is a supportive collaborative strategy. In the end, after solving the issue of the robot or the operator, we are returning on the independent task. Also, for the human case, where there is the opposite cases, where the human needs assistance because maybe during this operation needs a particular piece, and the robot can stop his task in order to assist the human, in order to help him, in order to facilitate the operations. The algorithm that we propose involves this experimental setup. So we have an OpenBCI instrument, which is an electrode helmet with the 16 channels. And also we are using ROS in order to create a program that is between the acquisition system and the collaborative robots. We have used a TM5700 as a collaborative robot, which features a high-end camera that can be used for visual servoing tasks. And for acquiring the data, we are using the SVEP techniques, which is doing a visual cortex analysis. So when the operator is focusing on specific monitors that pulse some frequencies, these specific frequencies can excite and become the EEG signal from the occipital lobe becomes stronger. So we can see the frequencies doing a Fourier analysis, a frequency analysis of the signal, and see that frequency that the monitor excites and the multiple of that frequency. So we can have a discrete signal from the brain, and we can notice them and we can use them. So for the case study, I want to show the algorithm that we have used, that is a general algorithm and a general schema. The interaction algorithm use ROS and the OpenBCI. There is an initialization of the system and the program of the frequency recognition. The first case can happen if, for example, there are no signal recognized by the SVEP. In that case, can happen that if the robot doesn't ask any assistance, so we are in the trivial case, so we are in the dependent collaborative strategy. In this case situation, nor the operator nor the robot require assistance. Instead, if we are reading something from some frequency from the helmet and the robot encounter an exception in its program, we can use the parameter, the signal read by the brain, in order to manipulate this task and send some commands. Also, the other case, the other situation, if the robot doesn't encounter an exception, we can use that parameter that signal in order to execute a specific task. In our case study, for example, we are using the in-hand camera can see the object, and we are using the signal from the operator in order to give the direction to the robot in order to find the object. So we associate to any frequency a specific direction in the plane in order to find the object. So we can move the robot in a specific direction using that signal. Or the other case, supposing that we need a particular object where the operator has busy hands, and we want to tell to the robot, pick me an object for me, or execute some particular task. The operator can provide the choices looking to the monitor. So can look at a specific monitor, which is programmed for a specific task. In conclusion, we can say that an hybrid implementation of collaborative strategy has been proposed, in which the operator can effectively assist the robot and vice versa. Also, the BCI device has been exploited and for driving the robot task by means of the SVEP. And it is important to underline that only two sensors are used for interacting with the robot, because For having signal from the occipital load, we need only 2 electrodes on the occipital load. And we can say that 2 case studies have been implemented for creating this supportive collaborative strategy. And in this situation, we have a mutual interaction between the cobot and the operator. This algorithm is quite general and can be applied for any kind of implementation of subtask triggered with these specific frequencies. If there are any questions, please ask. Thank you for your attention.
Thank you very much for your talk. Is there any question? Comments or remark? Federico, are you a graduate student?
Yeah, I am a graduate student of bachelor, but now I'm graduating in Master of Science in Mechanical Engineering.
So that study has been produced from a project, or?
Is another project, is not my thesis.
So what was your task exactly in this study?
Well, I developed part of the communication between the VCI and the robot. I studied ROS for my thesis, so I involved my knowledge about ROS with Python programming and C++. And I programmed part of the interaction strategy, which involves to use the frequencies and associate that specific frequency to send a command. So I programmed that particular part of the task.
So one of the others is your supervisor?
Is Marco Carnevale.
Yes. Okay.
Yeah, good morning. Just to say that Federico is going to join our lab at University of Pavia. We're trying to, we are both, me and my colleague Giberti come from Politecnico di Milano, and now we're working in University of Pavia trying to set up, let's say, a laboratory based on industrial automation and robotics. And so hopefully Federico will join us the next year in the PhD.
Congratulations. Thanks again for your presentation.
Thank you so much.
Title of the next talk is Autonomous Driving by Using Convolutional Neural Network. The speaker is Dr. Nicola Kalkovaliev.
Hi, Emir. Good morning, everyone. Let me just share my screen first. Okay. Can you see my screen at the start, just before I...
Right, you can see it.
Thank you. Well, thanks, everyone. Thanks for joining this morning session and staying till now to sort of listen to my presentation and our topic. This topic and this thesis that we did is my bachelor thesis, and it was mentored by my professor, Georgina Mircea, from the Faculty of Computer Science and Engineering in Skopje, Macedonia. So big thanks for the mentorship and the support to kind of present and go through this with this topic. Okay, before I start with the actual topic and presentation, I would like to sort of share with you a couple of words how this started, how this journey of ours started. Well, I would add that today in the trend of the world in machine learning, we have a lot of interesting trends, and one of them is this autonomous driving. And I would say the main motive and drive behind this research that we did was sort of to see how can we apply these latest trends and how can we use them in something similar and based on what, let's say, hardware and resources we have. And that was the main drive and goal. Sort of, we went through discussions and research related to pros and cons of this autonomous driving, because as maybe some of you know or don't, there are pros, but also there is this cons stuff that are sort of a field of interesting discussion between researchers and people who actually work on these fields. But as every new technology out there that is making its way, we have the benefits. There are sort of outweighing these consequences or these bad stuff that came up from that technology. So yeah, the curiosity and the motive to check and do something on our own related to this was our main goal. I would like just for a start to mention the content of this presentation. First, I would go with a short overview of what a convolutional neural network is. I would just mention the libraries that we used, sort of if someone likes to sort of play with this maybe in the near future, just to have a glimpse of what is used actually. And the third part will be focused on our project for autonomous driving by using a convolutional neural network. Convolutional neural network, what it is? Well, it's a class of deep neural networks. They are mostly used in deep learning, which is, as some of you know, a part of most of the bigger field that is actually called machine learning. And they are mostly applied and used for analysis of visual pictures. And their wide range of uses goes from pictures and visual recognition, natural language processing, recommendation systems, and stuff. On the left picture, we have a basic standard neural network. As we can see, and these standard or basic neural networks are consistent of a single vector for that input layer, which they transform it later by a series of hidden layers. In our picture, we have only two hidden layers, just for purpose of demonstration, but it can have a bit more. Every hidden layer, as we can see, is composed of a set of neurons. Those white spots are called neurons that we see on the picture, and they are fully connected to all the neurons from their previous layer or the layer that is behind. These neurons inside a single layer function independently one from another, while the last fully connected layer is known as the output layer, or that is the layer that is giving us sort of the desired, let's say, answer to a certain question that we want to sort of put through this neural network. All these layers are fine, and they should do a simple job for sort of some of the tasks that we are going to give to this neural network. But a problem will came up when we want to scale, let's say, pretty much bigger pictures that have some let's say it like that, bigger width, height, and depth. And this would create sort of a scenario that is called an overfitting, where the neural network will try to sort of process it through, let's say, a bigger number of weights that will be put as an input. Well, how this is sorted, we have the convolutional network that fits this standard and solves this issue. The picture on the right side that we have is a depth, height, and width, and the convolutional neural network with its kind of architecture enables us to have neurons structured in 3 dimensions, width, depth, and height. On the next picture, we have a simple, let's say, a simple convolutional neural network that is handling or is processing a handwritten digit. We have for an input, we have the first layer, that's the input layer. Next is the first convolutional layer. We have the max pooling layer. We have once again the second convolution layer, max pooling layer, and the ReLU activation of the fully connected layer. And as the last layer of this architecture of convolutional neural network, we have the output layer that is sort of making up these results based on what handwritten digit was put as an input. For this particular scenario, suppose an output will be number 2 if the convolutional neural network or the model is well trained. That would be just a short overview and glimpse of this. I wouldn't take much of your time related to this because that's not our focus. These are the libraries that we used. The language, the programming language is Python, and this Matplotlib library and some other libraries from Python that I hadn't mentioned, just to make it more straight this slide. But we have other libraries, mostly for graphical representations that are used, but the most important ones are TensorFlow and Keras, which are part of these machine learning packages that are mostly widely used nowadays. The specific versions I can just send to you or something like that, but just ping me out on my email and stuff like that, but that's not the focus of this presentation. Okay, let's go to our main goal, or what we did as our project for autonomous driving using a convolutional neural network. I will start with a simple intro, what we used as a simulator or as a data, how we approached to solve this problem, how did we choose our training data, and the last chapter will be focused on the methodology of training and validation of this data. As an intro, I would say, because this research is heavily based on an NVIDIA paper that they did, where they actually put cameras inside the driving vehicle, and that they recorded that actual data, and that data was later put inside a convolutional neural network, on an architecture that we will see later on in the slides. But as we cannot actually multiply that or emulate that, because it's a bit financially not applicable, and it's sort of an effort that takes a lot of time, a lot of people, and a lot of resources. We started by using this, we found this Udacity course on the Udacity platform that is giving us this self-driving simulator. What this self-driving car simulator for Udacity is giving us, that it's giving us 2 tracks where we can sort of drive the car on these 2 tracks. In the first mode is the training mode. With this mode, we collect our data. Basically, we record our driving on a specific track, while the autonomous mode is that second part of this process of ours, where we just run our model in the autonomous node, and the car will start just to drive itself, because the model and that we generated will learn sort of to drive on this track that we previously trained the model. So this is how it looks. This is basically the record model of the simulator. Yes, as I mentioned, we use it just to collect our training data, because we cannot emulate this in a real scenario, because we need resources, we need finance and stuff like that. And this is the most applicable way that we found that we can do this. On the next slide, this is our strategy or our process of collecting our data. As we can see, at the top is this Udacity simulator that is composed of 4 components. The first component is the steering angle. Basically, when we drive the car, with every, let's say, action that is put through the specific arrows on the keyboard, let's say we want to go to the left, we press the left arrow, and that steering angle that is applied on the car is sort of recorded in the same line with the left camera that is mounted on the left side, the central position camera on the car, and the right hand side of the camera. And basically these 4 parameters are stored as a single picture. Basically we have a left camera with the steering angle, we have a central camera and right camera in a specific time frame that are stored in a drive, and that is later used as our training data. How this training data of ours looks? Well, these are screenshots from the left camera, the central camera, and the right camera on a specific or on a certain point of time in the track. Well, the question that rises after we collect the data, let's say we put the car in the training mode, we drive towards the track, we hit the record button on the simulator, and all this data is stored. But the question is this training data of ours that we have right now that is stored locally normally first, is this training data enough? Well, no, this isn't enough. And what we do actually, how we solve this? Well, we use some of the techniques that are known. We try to augment the training data with the following techniques. As we can see on the picture presented, we take the original picture or the original image, we do the following techniques. We do a random flip. After that, we apply salt and pepper noise. After that, we do a random translate. We do a random shadow. We do a random contrast, X, Y, and V transformation. And as a final, we have final transform or crop. And these transformations are done in every batch where we generate this augmented picture so our model can sort of generalize better. Where we're actually doing this, a problem for storing these augmented pictures came to our attention because the whole process can be really expensive and can easily exceed our RAM capacity. For solving this issue, we used generator function, and with the help sort of this function, we store the augmented pictures on the RAM, but not all of them, but we stored on the RAM only the ones generated for that current batch of training. Next, we try to explain the training process, how we handle the overfitting with the use of dropout and batch normalization, and we will see the final architecture of the model. This is the whole training process. Basically, as I previously mentioned, the pictures that we stored will be our input with all those augmentations done. This will be the input to our convolutional neural network, while the output will be a predicted steering angle, so our car can react properly on every situation. The convolutional layers and the filter are compatible with this kind of problems because the convolution is mimicking the response of a single individual neuron into a visual stimuli, actually, that we need in that specific scenario. The training process of the neural network is simple, and yeah, as we can see on the picture, after, as I said, we augment the pictures with the techniques, they are taken as input into this convolutional network of ours, while the result is the predicted steering angle. The weights in the convolutional neural network are adjusted so they can bring the output of the neural network closer to the desired output. In our study that we did, the weight adjustment was done using the backpropagation implementation from the TensorFlow and Keras libraries. This is the distribution of our training sample data, and this picture that was designed shows us that on the horizontal axis, the y-axis, the angle of rotation is shown, the angle of rotation of the steering wheel presented in radians, while on the vertical axis, we show the frequency of occurrence of that angle in the samples. So how good is actually our model? Well, for us, in order to check how well is our model working, we have split the data from the pictures and angles of movement of the steering wheel into training and validation sets. The data in the series from 1 to 4 are generated from the generator function. So the batches that we see in every series are chosen randomly from the whole set without repetition. It is worth mentioning here that all of the operations that we mentioned above for picture augmentation are applied for our training set, while for our validation set, we use only flip and crop operations. Here we can see that the distribution and the distribution of the training and the validation set in each batch. For our parameter adjustments, no manual adjustments are used, but we only use the Adam optimizer. Well, after we created the first model, we discovered that that our model had a low mean squared error on the training set, but a high mean squared error on the validation set. This led to the conclusion that our model is overfitting, or we had a case of overfitting. And how we solve this? Well, we applied the technique of dropout and batch normalization. The batch normalization technique we use to increase the stability of the neural network model because, as it's known, it normalizes the output of a previous activation layer with subtracting the batch mean and dividing with standard batch deviation. Well, also the batch normalization reduces the overfitting, similar as the dropout technique. It adds some noise on every hidden activation layer. So if we use batch normalization, we will use less dropout. This is actually a good approach for us, and since we won't lose too much on information. However, we should not depend only on batch normalization for the regularization stuff, but we should also try to use them in parallel with dropout for better results, as we did. Additionally, batch normalization accelerates the training because it requires less iteration, so it can converge towards given loss value. This is the final architecture of the model that we did. As I mentioned, it is based heavily on the NVIDIA's end-to-end learning for self-driving car architecture. These are the layers presented that we have, the input, how much neurons, and how batch normalization technique is applied in every convolutional layer that is out there. This is the performance of our training, of our model during training. As we can see, the number of epochs that we did for training was 18. And with the use of the ADAM optimizer, we met manual training of the learning rate, not necessary in our case. We had a total data set that counted like 47,000 pictures, and we chose only 80% from them, so we can use them as an entry into a training set, while the remaining 20% of that pictures that we have as training data was used in the validation set. Here also we show the performance of the model when training up to 18 epochs, as I said, and the mean squared error loss in every epoch is shown if the model is tested with the use of the training and validation sets accordingly. From this picture, we can see that the mean squared error loss during training is declining as the number of epochs is increasing. The results show that the model is able to accurately generate the angles of our desired steering wheel. Also, there is no significant difference if you use training or validation set for testing. This indicates that the model is not overfitted and is able to accurately make predictions for unseen samples. This is just a picture of how the convolutional network model combined with the trained model. And as sort of end to our presentation, I would like to show just how the autonomous mode is working. Basically, as we can see, this angle is the output of the convolutional neural network. The mode is autonomous on our simulator, and our car is just driving itself right now on the simulator. As we can see, when it goes towards those border lines, it just shifts towards the center because we trained her to do so based on our training set. Also, this is the part where we train it with the same model on that second layer, on that second flow that we had. And yeah, here I would end my presentation. And yeah, I would like to thank everyone for your attention. It took us some 5 minutes longer than expected, but yeah, it was an interesting part. I don't know, something to ask, maybe stuff like that.
Thank you very much for your presentation. Is there any question, comments, or remark? No question. Everything is obvious. Thanks again for your presentation. Okay. The title of the last talk is Impact of Environmental Variables on the Propagation Phenomena in Wireless Sensor Networks, Open Problems and Research Opportunities. Name of the speaker is Mauricio Gonzalez Palacio. I think he's absent. He sent me a message that unfortunately the network and connection is not very good in Colombia right now. So he's absent. He's very sorry because of the fact that he cannot present. Okay, thanks again for your participation in this special decision. So I'm ending our decision. Do you have any questions? Okay, thanks again for your participation.
Thank you, Dr. Mohammed.